And thank you very much for the invitation. First time here. So I haven't had time to explore. I landed 6 hours ago, so it's very new yet. So I'll mostly use this. So I hope my handwriting will be fine. Maybe one thing, what Christian said, that this is not really math finance nor the other mini course. I actually disagree with that statement. I like Christian, but we agree to disagree often. Because math finance is actually a very exciting area where you can do any kind of math as long as it serves a good purpose. Right? We have real life problems, and any tool that helps solve them is a good tool, right? And that's the exciting part of it, right? We're not limited to say, oh, we only do stochastic analysis. The fun part is actually to look at different areas. Okay, so normally if I do this, that works, yes. Okay, so I'll be talking about quantum computing so the main goal is with applications to finance. As you'll see, the application part is, will be slightly limited. First, because I only have 6 hours and can't do too much in 6 hours. And also because, the reality is, okay, I could start my speech by saying, okay, the goal of the 6 hours is to convince you that quantum computing will solve everything, and you don't need this, fancy Mac laptop or not Mac laptop and all that, right? But that's not the reality. It's a nascent technology. We have some tools, but this is actually our goal on the math side to explore what we can do with it. So the goal of this lecture is to, first to give you the tools to understand a bit this quantum computing literature, which is most of the time for now written by physicists and computer scientists. Before I say bad things about these people, who has a background in physics? Okay, who is more math? Who describes himself as more math than anything else? Okay, I'm in safe hands, so I can say bad things about physics. Good to know. All right, so let me just give you a quick. So this is quantum computing. It works. So the idea would be what? So this is not a physics course, but as I mentioned, so of course, this is quantum computing, meaning it is related. Don't worry, it will be more precise later. This is related to quantum mechanics and quantum physics, but this is not a course about quantum mechanics or quantum physics. Right? Quantum mechanics is, if you wish, the background where it originated from. But quantum computing, it's computing, right? I'm not doing philosophy. I'm not looking at atoms. I'm looking really at the computing part. But of course, that's the original motivation. And what we will look at in terms of applications, we'll look at 3 aspects. One is optimization. So there's no particular order. Well, what I'm writing. One is machine learning, and let's say one is Monte Carlo. So if I were a very diligent speaker, I would say, well, because the conference is stochastic numerics, I should spend most of my time on the Monte Carlo part, right? But in fact, I can even play with colors. I won't talk about this. But there's a reason for that, not just because I like offending people in general, but because quantum computing, we'll make all this more precise later, but there's, let's say, the ideal world, and let me not use this word for now, and the reality. And the ideal world says, I actually have access to a full-scale quantum computer, big one. For now, I'm using very vague words like big and full scale, but we'll make that more precise later. Think of it as I have access to a supercomputer, so in principle, I am able to run any kind of computation, right, for as long as I want. And some algorithms, so you may have heard of Shor's algorithm, of Grover's algorithm, which are basically factoring prime number factorization or finding an element within the set of n elements where we have exponential speed up, or not always exponential, but at least quadratic speed up compared to classical methods. And these algorithms, so they date from the 1990s. Sorry. I can write again. From the 1990s. So I'm just writing the names here. There's Grover, there's Shor. So Shor is to do prime number factorization, which of course is extremely important because it's at the basis of cryptography, right? Grover's algorithm is to find one element among a sequence of n. And these were written in the 1990s where they proved that there exists, assuming that I have this big supercomputer, there exists an algorithm I can run on it that will have clear speed up compared to classical algorithms. When I say clear speed up, I mean, depending on the cases, either at least quadratic speed up, sometimes exponential speed up. And basically all these algorithms rely on techniques, in particular, like this, QFT. This is not quantum field theory, this is quantum Fourier transform, which is a way of writing Fourier transform in the quantum world with an exponential speed up. The problem is, in order to realize these algorithms, in order to implement them, and to actually see the speed up, we really need large-scale quantum computers, which we do not have today. By the way, so I'm using this for now, and then we'll have a break. And after the break, at some point, I'll switch to laptop to show you some pictures and I would do most of it here, all the math here, and then the pictures I will show them later. So right now, we do not have these capabilities. So we cannot run efficiently quantum Fourier transform, for example. We cannot run efficiently these algorithms. So the reality is we have small-scale quantum computers. And the question is, well, first of all, they don't work exactly the same way as your Mac, as my Windows, so on. So there's a special type of algorithm that I can run on them. And because they're not full scale, I'm limited to the capability of the computer. So what kind of algorithm can we actually run on them? And this is the reason why I'm not talking about Monte Carlo here, because I'm interested in what we can actually do now. So when I say now, it means now and at least over the next 10 years, right? This is not really achievable according to people who actually build them within the next 10 years. But I know, it's progressing. Sorry. But this we can already do on reality. Reality means current quantum computers and the way they are being developed right now. Okay, so that's the idea, right? So the structure of the course, I will spend a bit of time in the beginning going through the formalism of quantum computing, what it looks like. In some sense, the math involved is mostly linear algebra. So if you hated linear algebra in undergrad, too bad. And then in the second part, so tomorrow, we'll look at the applications, in particular optimization and machine learning. So that's the general idea. So bear with me, at least in the first part of the course, where we go through funny notations and all that, but they all serve a purpose. Okay, so if I scroll down there, yes. Okay, so as I said, quantum computing originates from quantum mechanics, right? So, and quantum computers, the way they build, it's to harness the philosophy and the principles of quantum mechanics. So there's a certain number of axioms or postulates, how they call them, that drive the computations. So let me see. Works. And tell me if you can't read my handwriting. So postulates of, so this funny Q is quantum as opposed to quantitative so I mean, right, quantum mechanics, but in fact, this applies to quantum computing. Maybe one thing on the, well, no, I'll tell you later. I don't want to spoil it yet. So postulate one. So by the way, I'm here the whole week, right? So of course on the board and on there's loads of things I cannot write, also because of time. So if there's anything you want to discuss later, if you want any particular references and so on, of course, feel free to ask. So postulate one is the state space of a quantum system of a quantum system is a Hilbert space. Curly H. So in principle, pretty much everything, modulo a few technicalities, can be done in an infinite dimensional version, but because we do computing, everything will be finite dimensional. So the state space is a Hilbert space, and a quantum state, is so let's write this. First is a vector in H. And in fact, I should say, is a unit vector in H, which is not completely correct. In fact, one should say it's an array. And I'll explain that why in a second. So start with the simple case where n is equal to 1. So n is equal to 1. So classically, the basis of information is a bit, right? A classical bit. In quantum computing, the essential piece of information is a qubit. Maybe I should write it. So this is a 1-qubit system. And in that case, H, the Hilbert space, is just a complex space. And let me write 2 to the 1. Which is C2, of course, but just so that you see that the n will be what appears there. And so quantum state takes the form. So let me write it U. So this is Dirac's notation. So this means ket U. KET. And I can write it like this, where alpha and beta are complex, and modulus of alpha squared plus modulus of beta squared. Maybe that's right because they're complex, right? So alpha star plus beta star equals 1. Sorry, it's a bit squishy at the end. It's modulus squared, it's not the absolute value, right? And what are the 0 and 1? Well, this is the basis of C2. So 0 is just this vector, and 1 is the other basis. That just describes the vector in C2, right? Why did I write array instead of vector? because the point is, if you define V to be e to the I theta u for theta real, it means that u and v are indistinguishable. Right? So the general phase outside doesn't matter. And this is the definition of a ray, right? So let me write like this. Right. Because it's a ray, I should not be able to distinguish the two vectors, the two states. Okay, so that's the first postulate. Second postulate, fine. Of course, if you have any question, I guess you are allowed to ask. Yes. Well, one answer is because it gives you more flexibility, more generality. And if you don't have complex numbers, there's no quantum speedup. And actually, somehow the beauty or the interest of quantum computing is because you have complex numbers. We'll see why later, hopefully. But if you restrict everything to real numbers, then this is just classical mobility or classical algebra. You don't get any gain from it. I'll give you one example in a minute. If I don't, remind me. But I need to introduce a few things first. Postulate 2 is a quantum state, well, or the evolution of a quantum state runs through unitary, this is a weird sentence, runs through unitary operations. So what do I mean by this? It means, so here we're doing finite dimensional linear algebra, right? So again, so U is a unitary matrix in H, but H really will be of the form C to the 2n. The n in general will be the number of qubits. So for now, we only looked at the n equal to 1 case, but we'll generalize it soon to the general n. So U is a unitary matrix. Just as a reminder, it means that U dagger U is equal to U. This is multiplication. U dagger equals identity, and U dagger is defined as U transpose star, complex conjugate. But as a quick comment, this means also that the inverse exists and is equal to U dagger, right? By definition of the inverse of a matrix. So the evolution of a quantum state runs through unitary operation. It means what? It means that if I start from a quantum state U, so of the form alpha 0 plus beta 1, as we had before, the only way to modify U, well, let's say U0 and go to U1, well, let's write it. Think of time, right? So U at time 0, and I evolve it to U at time 1. The only way to do it is through the action of a unitary operator or a unitary matrix. That is the only way you can transform qubits. Geometrically, what it means, well, if I take C2, this is the unit sphere, right? So a quantum state is just a unit vector on the unit sphere, and U will just be a rotation matrix. So that allows me to move anywhere. Don't ask me to draw a sphere, right? I'm very bad at drawing, but this is a sphere, right? So I can move my unit vector. Let's say I start in the upward position. I can move it anywhere on the sphere by unitary operations. But unitary operation in C2, these are just rotation matrices. Okay, now let's say P2 prime. This P2 is the quantum computing version of evolution. P2 prime is the quantum physics idea, which is a quantum state evolves through Schrödinger's equation. Which looks like what? Which looks like this, I dt. I prefer Greek letters, right? So hope you don't mind. H psi of t with some initial condition. What you want? So I is complex I. Psi of t is a quantum state at time t. And H, now here, so I apologize, H appears in many places because, well, there's H for Hilbert, and there's H for Hadamard, and there's H for Hamiltonian. Well, not my fault, right? So here H is what? So in general, this could be infinite dimensional, so this will be a Hamiltonian operator. But here, so H stands for both Hamiltonian. But because we are in finite dimension, this is just a Hermitian matrix. Hermitian. Matrix. And as a reminder, Hermitian means H dagger is equal to H. So the first one, we'll see that later. This is really how every computation that we're going to run on the quantum computer, and I'll show you some code later just to make it a bit more practical. This is how it works. But Schrödinger, that was 100 years ago, roughly. He's from Vienna, right? Okay. So he always pleased the organizers. Said that the evolution of a quantum system evolves like this, right? So now you can wonder actually what's the link between the two. And this is not just informative, but useful. I don't know, let's write it as a lemma. A badly written lemma, but it's an if and only if. So e to the I alpha h is unitary for alpha real, if and only if. This is bad. No, this is correct. H, if and only if H is Hermitian. So here, I mean, again, I might talk about operators, but they're really matrices, right? Because everything is finite dimensional. If you don't trust me, that's a two-line proof. It's one direction is easy because if H is Hermitian, if H is Hermitian, then I'll take this dagger, right? The I is I is real, so this is, I'll go minus and h dagger, but h dagger is h. So this is just e to the minus I alpha h, which is the inverse. So then it's u dagger is u minus 1, which is exactly what you want. The other way, you have to work a little bit, but it's really a one-line proof. I'll leave it as an exercise. So why am I saying this? Because of the following. So let me rewrite my Schrödinger equation. So here, you should have said h is not time dependent. H does not depend on time. In general, it does, but I want to make my life and your life easier. So this is just an ODE with some boundary initial conditions, so we can solve this. You can even do it by hand. This is e to the minus I h size of 0. Okay, this is an ODE. Yes? H, so in general, according to Schrödinger, this is H is some Hamiltonian operator. Here we do everything in finite dimension, which means H is a Hermitian matrix. So here, psi of t, in our case, that would be a vector in C2 to the n. This is a Hermitian matrix, 2 to the n by 2 to the n, and that's it. And this lemma only relies on the fact that H is Hermitian. So, of course, this ODE, we can solve it, right? So this is the matrix exponential. And, oops, times t, obviously. Sorry. But, okay, the lemma just said that, in fact, this is the same, this is unitary, right? Because t is real, t is my alpha, I is I, h is h. So this is unitary. So it means what? It means in the end that the evolution of a quantum system, or a quantum state, runs through unitary operations, which is exactly postulate 2. Now, so that's but the reason I'm mentioning both is that because of the application we'll be looking at, both formulations are actually useful, but they are equivalent. All right, postulate 3. And I have no idea about time, so you have to tell me at some point. Oh, plenty of them. Okay. As you'll see later, if you don't stop me, I can go on I won't stop. I can go on until tonight, until I collapse. This is too complicated. It's not good for my neck. No, but there's one there. Okay, it's easier. So postulate 3, this is a tricky one. This is a tricky one because this is really where, well, not really too much anymore, but what people have been disagreeing for a very long time with quantum measurement. Incidentally, in the plane a few hours ago, I watched Oppenheimer, which was a lot related to quantum physics. So this was very topical. So, okay. So the reason why I'm saying this is the tricky part is because this is where, for now, this is just, okay, some notations and some definitions. This is where really the quantum part, especially 100 years ago, or 1930s, 40s, there's a lot of disagreements. So quantum physics and quantum mechanics quantum physics originated in the 1920s, right? And which was basically to explain how particles work, right? How they interact and how they evolve. But a lot of people, including Einstein, for example, never agreed with this interpretation and with this explanation. And so quantum measurement, so how does it work? So we have access, basically we have a collection of measurement operators little m, with some little m is just an index, satisfying what's called the completeness equation. Yes. Been realizing that it's not an issue if I hide the board, right? Because in fact it's there. Okay, completeness equation, which is what is the sum of all m dagger, is identity. So I will always be identity. Whenever I don't specify dimensions is because it should be obvious. But of course, if it's not clear, let me know. And n corresponds to the outcome of the measurement. We'll try to make that clear in a second. Okay. So next definition, this all go together in this P3. Physical what? A physical, what? For now, no. For now, no. But the next item will make that clear. This is very general. In fact, it's rarely used in this generality. It will be mostly used in the next bullet point. So physical reality corresponds, or we can associate your physical reality to an observable let me write here, Hermitian and this one I call M. And because it's Hermitian, we know we have vector theorems for normal operators, means both for unitary matrices and for Hermitian matrices. But in particular here, it means, so this is a spectral decomposition. Some M, and let me write like this, lambda M PM, where PM is what is the projection onto the space band this is written a little bit informally by M. I will make that clear in a second. Okay, what's a physical reality? So the terminology really arises from these discussions they were having 100 years ago. And if you ask me precisely, I try to read the papers. I'm not sure I really understand them, to be honest. But I think, so I don't like analogies in general. I've become very loud suddenly. I don't like analogies so much in general, but I think one analogy that at least I vaguely understand, or I've made peace with it, let's say, is, okay, suppose you have the board there, right? And you have an ant, a little creepy crawly that runs through the board, right? But it's pitch dark. You don't see anything, right? So you don't know where the ant is. And the physical reality here, that we'll have two physical realities. One is the ant is on the left side of the board. The other one is the other one is the ant is on the right side of the board. Right? So I have two possible locations for the ant. But because it's pitch dark, in principle, the ant, and this is what we meant when we wrote this. We wrote this. Yeah. Here the ant is in a superposition. Let me write. This is an important word. Superposition. It's in a superposition of on the left side and on the right side of the board. Because it's pitch dark, in principle, it could be anywhere. But in fact, the quantum formalism is in both sides at the same time. With some probabilities, if you wish, but I'll talk about probabilities in a second. But now the physical reality is an observable. And what they mean by observable, what we mean by observable is really observable. It's pitch dark, so I don't observe anything. The way to observe is I turn the spotlight on the left-hand side of the board, right? That's the projector. That's it, that's projector. Projector on the left side of the board. Or I have another projector, which is the right side of the board. Once I apply this projector, basically I pin down the location of the ant, either to the left or to the right, and I observe whether the ant is there or not. It may be or it may not be. So, but of course, in general, I have my projector, right, which allows me to observe everything. But the point is, I cannot use the whole projector. I only have access to projections onto some subspaces of the whole space. And so I have two locations: the left side of the board, the right side of the board. Let's say m is equal to 0, m is equal to 1, and this is a projection onto the left, projection onto the right. Of course, spectral decomposition. So the actual values that I can observe are the eigenvalues of the Hermitian matrix. Now, one thing that's important is because it's Hermitian, the eigenvalues are real, right? You don't remember first year undergrad, easy exercise. And this is important because the eigenvalues of the observable are the actual values that you can observe your quantum state in. All right, so here again, the analogy is that big M is my observable. Yeah? No, it doesn't. Big M is my observable, and I have two, which means that I can observe two possible values for the quantum state, lambda 0 and lambda 1. I may have written M, but yeah, M lambda M is just the index, right? So I have two possible values that I can observe my quantum state in, lambda 0 and lambda 1, and I will be able to measure them or observe them by applying the projector P0 or the projector P1. Yes. Well, that's because I took this example, right? But in general, I have in general, if I have n qubits, well, we'll come to that in a second, I have 2 to the power n values. But here, this is just a 0 and 1, right? Just to make it easier. But we'll see For now, we're only thinking of 1 qubit, n is equal to 1. Therefore, I have 2 possible values. So let's look at an example. Oh, no, I should say, no, before that, let me add 2 more things, and then I'll look at an example. The probability of observing or measuring, observing and measuring are the same. Measuring of observing M is PM. I will explain the notation in a second. I'd rather introduce the notations as we go along, as we need them, rather than all in bulk at the beginning. So here, psi, we know what this is, but this is a quantum state, which in general is just this. Which, of course, if I want to write it as a vector, I can write it like this, but it's a bit squeezed on the right, because ket 0 is just vector 1, 0, and ket 1 is an alpha beta complex, and modulus of alpha squared plus modulus of beta squared is equal to 1. Right? But trust me, in fact, when I first started looking at quantum computing a few years ago, I found these notations very cumbersome and not handy, but they turn out to be very handy, actually, especially when we look at large systems. Now, so this is a ket, we said. And now I can define a bra, which is the other, which is ket psi dagger. Right, so here, if you like matrices, this would be this. Right. But it also means that physics people are so cool, well, because then this is a bracket. We agree there are not many physicists, right? So I can make fun of them a little bit. Right, so, sorry, but I mean, this bracket, right? So in principle, we should write, I have the bra and the ket, right? So this dot here, this is just matrix multiplication, right? Or vector multiplication. But in fact, we have 2 bars, so this is not very nice. So we just put 1 bar, right? And this is clear from the context. And now this is just an inner product in my Hubble space. And so this is a bracket, because I've got the bra and the ket. Okay, so now here, come back to here. So what this says, of course, I can write this slightly differently. I can write that this is psi dagger times psi, which is simply psi. Right, no. Right, so here, these are dots. These are just matrix multiplications, right? And the dagger or the transpose, you invert, swap the yes. So here MM, these are my MM. It's a collection of measurement operators. And if you give me 1 minute, I'll make the link with this. But here MM, so the important thing here is I have a collection of operators. Again, think of, that's a way of observing the system, right? So I have a way of observing the system associated with some value M. And the probability of observing the system, so here, when I say the system, I mean the location of the ant on the board. I can observe it with this probability PM, which should be this should be a definition, part of the axiom, part of the postulate. Let's try to make, do I want to say anything else about this? Probably not. Well, maybe I can, yes, maybe let's add one thing. If I have an observable well, let's keep it for later. So let's look at an example. So, and the example I'm going to take is really, I have the left side and the right side of the projector. Yeah. Here, well, it could be 2, let's say 2 to the n by 2 to the n. But here, yeah, 2 by 2. And positive. Yes. Of course, there, it's not obvious that it's less than 1, but it is less than 1, but essentially because of this completeness equation. Right? Because this, in fact, is the sum of the PM. Really. But this is, yeah. I mean, so if I look at this, right, we can, let me just rewrite this. If I look at dimension, let's say I'm general n is an integer, right? So this is a column vector. So this is 2 to the n 1, the dimensions, right? 2 to the n rows in one column. This is 2 to the n by 2 to the n, right? So this is 2n to n. I mean, the dagger doesn't change anything. And this is the transpose conjugate. So this is 1 to n, right? This is in dimension 1, and because I have this is a real. M is 2 to the n by 2 to the n. Oh, this is a general Hermitian matrix. But the point of a Hermitian matrix is the eigenvalues are real. The point of a Hermitian matrix is the eigenvalues are real numbers. So the probability of observing the eigenvalues are the values that you can observe. And they are real. And now why, I can really interpret them as probabilities. Well, first, because they're positive, non-zero, obviously. And the fact that they sum up to 1 is this completeness equation. If I sum all, well, maybe I can write it, right? If I sum over M all the probabilities, this is the sum of psi, MM dagger, MM psi. Right, then by linearity, this is sum MM dagger, MM, to the brackets like this, psi. This is psi. This is the by completeness equation. This is identity. So this is just psi. But psi is a unit vector by definition. So this is equal to 1. Sorry? Well, in general, it would be, you know, I have 2 to the power n eigenvalues in general. So here, okay, in my particular example is 2, right? But it's in general, it's 2 to the n. No. Well, as you can see, clearly, I mean, for this probability to be 1, the only thing it does, in a way, is that the observable here is relative to psi, in a way. But I always struggle a little bit with that, with some of the conceptual definitions somehow. Here, you know, the quantum state I described my ant, in my analogy, that was the location, right? But of course, I could look at another property of the ant, right, which will also have a quantum behavior. And so that could be another one. But I can also change the basis, right? Here I took 0, 1 as a basis, but I can take another basis in C2. And of course, that will give me another psi, but in the end, the computation will remain exactly the same. Example, right? Maybe let's do a little fun computation first. Remember, 0 is this vector. Ket 0 is this vector here. So we know how to do this. These are not smileys. This is like this, right? This is just 1. I told you technically it's not too hard. So this is the inner product, right? Sorry? Exactly. This is an inner product. But I can also define the outer product. Which would be this. So let's just rewrite those matrices just so that this is familiar. Right. So this now is a matrix. Right? Easy peasy. Okay, so now I can define 2 projectors, P0 and P1. And what? And so let's take a quantum state psi. So in general, it has this form. And so what do I want to say here? Let's try to compute this quantity. Psi P0 dagger P0 psi, which would correspond to our little P0, right? If I view P0 as my measurement, where little m is 0. Right? So I use P as projector, but it's also a measurement operator. Well, okay, P0 dagger, right? So this is 0, 0 dagger, which is same as P0. Dagger, but everything is real, right? So there's no complex part here. And P0 dagger P0. This is P0 squared, but of course this is projector, this is just P0. So this is simply psi, P0 psi. So let's expand this. So drop psi, this is alpha star 0 plus beta star 1. Then I have my P0. Let's see if this makes it even clearer. So we have colors. Let's use colors. Right, so I'm just rewriting. So ket psi by definition is alpha 0 plus beta 1. And bra psi is the complex conjugate. All right, so alpha becomes alpha star. Then dagger of 0 gives me the row vector. And now, okay, so let's keep this one for now. Okay, and now, so this is written in terms of Dirac notation, but these are really matrix multiplication, right? So of course I can distribute. So I have 0 times 0, so bra 0, so bracket 0, 0. So 0 and 1, ket 0, ket 1 are unit vectors, right? So bracket of 0 is equal to 1 as a real number. And they're orthogonal because they form bases. So bracket of 0 and 1, this is 0 as a real number. Right. So in fact, this is just alpha. Right here, 0, 0 is equal to 0 as a real number. And 0, 1, sorry, 1 and 0. And now, of course, I can do the same here, which is 0 by 0. Inner product of 0, 0 will give me 1, and inner product of 1 and 0 gives me 0. So this is just alpha star alpha, which is modulus of alpha squared. Why is that computation important? Because in fact, when I write my quantum state alpha 0 plus beta 1, we said alpha and beta are complex values, right? So in general, they're actually called amplitudes. They are not probabilities. But in fact, what we see is that modulus of alpha squared is a probability, right? Which, and in fact, it's what? It's the probability of observing my quantum state in position 0. I can do the same if I use the P1 projector, and I'll see that beta's modulus beta squared is a probability of observing the quantum state in state 1. Okay. Any question on that? Yes.
The matrix which was M.
Yes.
Sum of lambda M PM.
Yes. Yes.
M
I'll get there. I'll get there. This was just the example parenthesis. So now, I started by saying, okay, we have a collection of measurable MM, but we didn't really say anything about them, right? And then we said, actually, the general observable is a Hermitian operator, Hermitian matrix. If it's Hermitian, then it means I have spectral decomposition. So here in general, the observable M will be my spectral decomposition. Here will be lambda 0 P0 plus lambda 1 P1, right? So here the P0 will be the M0 and the P1 will be M1. So the reason I introduced it that way is because the general definition does not really assume anything about the measurable, the measurement operators MM, but in practice, we pretty much always use projectors. Not always, but most of the time we use projectors, which have this particular form. And again, what's important is the completeness equation, which ensures that the sum of the probabilities are equal to 1.
I know where I should start this together. Right now with like, there was some sort of.
So you can do infinite dimensional operators, infinite dimensional analysis, yes. But because we do quantum computing, we don't care about infinite dimension. But I mean, of course, everything here works in infinite dimension with some, little, minor modifications here and there, but it works. I mean, my spectral decomposition, of course, in general, I could write it, this is an infinite dimensional operator. I can write it over, I have my distribution of eigenvalues and then P lambda, right? And then, but again, because we do quantum computing, this is finite dimensional. And so we only care about the finite dimensional aspects. Of course, so there's a slight difference in infinite dimension. Hermitian operators and self-adjoint operators are slightly different. Because, that would be the infinite dimensional version that you care about for operators is really the self-adjoint property, which has some slight differences with Hermitian operators. But okay, this is outside the scope of that. Okay, so the last thing I want to mention in this P3, which is, so as I said, a quantum state, psi, is again the ant when it's pitch dark in the room. So classically, we would say, oh, the ant is either on the left or on the right, but the quantum version of it, it's actually in a superposition of left and right with some associated probability, right? But in principle, it's both on the left and on the right. If you remember the analogy, Schrödinger's cat is both dead and alive at the same time. Once I open the box, I observe dead or alive. Once I project, I observe left or right. But so the very important part is before measurement and after measurement. Before measurement, I have a quantum state. Once I measure, I collapse to a classical state. So in quantum physics or quantum mechanics, you would call it the collapse of the wave function. But here what we mean is after measurement, let's say MM, the state collapses to the state psi, MM psi divided by square root of the probability, just to normalize. So let's write PM square root. Or let's write it in the way it would be written in textbook, which is this. The denominator is just your PM, right? So the important part is once I project, so think again as P0. So let's look at the example again, where M0 is just P0, which is 0, the inner product, and psi is alpha 0 plus beta 1. And of course, when I project, I get my 0, 0, my inner product, alpha 0 plus beta 1, which is just alpha 0. Once I project, now the point is, there's no more ket one, right? So it really collapsed onto one eigenspace. Okay. Yeah. Yes. Yeah. And another set of little m, and another little set of eigenvalues. Yeah. Well, you could say, this is a projector left and right, but I can take projector up and down. So we'll have different ways of measuring. So if it's up or down, then it's either up or down, right? It's not top left. Yeah, but so if I collapse, it would be either at the bottom or at the top. I'll still only have two. Yeah. I mean, I could have 4 if you really want to, but you cannot, because because once you collapse, there's no quantum state anymore. You can only collapse once. You can only. Well, no, because quantum mechanics tells you that after measurement, there's no more quantum state, basically. It has collapsed to a classical state. Yeah, it's not quantum anymore. So, okay, first of all, this is more physics and philosophy. Okay, one part of the answer is I don't enter this debate because I'm not a physicist, right? And I'm not a philosopher either. Well, at least not in the morning. The main consensus, if you ask pretty much any physicist, they all agree with, so this is called the Copenhagen interpretation of quantum mechanics. I think this is by far now the agreed understanding. You still have other interpretations, but this is very minor. So maybe I don't want to spend too much time on this, but this is the most agreed understanding. Also because basically all the experiments that have been done, physical experiments that have been done, agree with this interpretation so far. Yes. How does that work?
Okay.
Oh, this is cool.
Yeah, so quick question. You're using this operator
yes.
to measure, right?
Yes.
And you say that the collapse is on psi, psi, and essentially the result is a normalized vector, right? And you say that is a collapse already vector. So if I do it like this, what have I measured essentially in terms of information? What is it given to me? Is it the alpha, for example, if you project on that? Because when you normalize, you essentially get the vector that is aligned on the
Yes. So what you want, what you want is ideally to determine the quantum state. So you want to determine alpha and beta, right? This is your quantum state, this is your ant, blah, blah, blah. So you want to determine alpha and beta. Now, what we saw is that if you apply a measurement M0, you observe zero state, right? And the alpha. So now the way quantum computing works, but we'll come back to this later, is so I apply my P0, right? Let's say P0 is the left. And now practically I observe, is the ant there, yes or no? I know I can observe, I turn the light on, and I can see whether the ant is there or not. Because once I apply my operator, the quantum state has collapsed.
Okay,
but yeah, let me just finish the sentence. But it doesn't really tell me anything about alpha or beta when I do this. But I know that alpha squared, modulus of alpha squared, is a probability of observing the quantum state in position 0. So in fact, the way it works is I'm going to repeat the experiment many times, Monte Carlo type, and I will get an estimator for alpha squared. So I'm going to repeat the experiment 1,000 times, and 400 times I'm going to actually observe the ant being on the left, and that would be my Monte Carlo estimator for alpha squared.
Okay. Just I wanted to follow in the notation there.
Yes.
Because you said after the measurement the state collapses and is no longer quantum, right?
Yes.
But what is the actual measurement? Because I follow the notation there and I cannot see essentially what is the actual measurement. You say we're going to observe whether it is on the left or on the right, right?
Yes.
So where do I see this in
Well, you see there because, so here this is measurement, which is a projection operator, right? Mm-hmm. Onto the 0 basis.
Yeah.
And once I measure, right? So once I apply my...
On the right is the measurement, alpha times this.
Yes.
That's the
measurement. Yes.
Okay, that's what I wanted
to... sorry.
That's what I wanted to confirm. That
sorry.
The measurement.
Yeah. Yes. So this is the... Yes. Okay, sorry. Okay, and so the last post.
So maybe that's a good.
Just a short question: do we allow 0 as eigenvalue?
Sorry.
Do we allow 0 as eigenvalue?
Yeah.
Okay.
We'll see examples with 0. Yeah. So this is all fun, but this looks dangerous. So this is all fun, but this is 1 qubit, right? So 1 qubit, we can't do too much. So now how do we generalize? And this is postulate 4. So a general, well, how do I write it? If I have 2 systems, the way to combine the system is by tensor product. So how do I write this? Given 2 quantum space, this H, A, and HB, right? So 2 Hilbert spaces, right? A quantum state on both. This is badly written, but I'll blame it on the recent landing. Lives on the tensor product of the 2 spaces. Let's see an example to make that a bit clearer. So, for example, I have, these are very simple. This is a quantum state in system A and a quantum state in system B. Alpha is equal to 1 and beta is equal, alpha is equal to 1 and beta is equal to 0, right? It's not very exciting, but okay. So the way to have, so this is n is equal to 1, n is equal to 1. So the way to have an 2 qubit system is by taking the tensor product of them. Usually, because of course you don't want to write tensor product everywhere, you would just write it like this. And it's implicit that this is a tensor product. And so just to see how that works, tensor product in linear algebra, that would just be the Kronecker product. So this will just be what? Or maybe just in case you don't remember, these are two matrices, right? This is A, 1, 1. This is a block matrix. A, 2, 1, B, blah, 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 blah. A, whatever it is, MN, B, right? These are block matrices, right? So here, that would just be 1, 0, 0, 0. It's just in case you haven't done that for a long time. And I have not either. This is multiplication, so this is 1, 0, 0, 0. Close it properly. Okay. And so, of course, now this is, of course, it means that 0, 0, 0, 1, 1, 0, 1, 1. This is an orthonormal basis of, obviously, C2, tensor product C2. Or my, if you wish, HA, HB. Yeah. So now there's an important, so take a quantum state psi. A 2-qubit quantum state. So let me write it this way. So 2 qubits means C2 to the 2, right? So C4. And there's, so if there exists, let me write it this way, UA and VB. Well, again, I mean, A is one qubit system and B is 1 qubit system, right? So if I have two quantum states, one living in HA, one living in HB, such that psi can be written as the tensor product, then psi is not entangled. This is an important keyword. I will explain that in a second. So entanglement is really at the core of quantum mechanics and quantum computing, and this is where any speed up, any quantum speed up will arise. So essentially, maybe let me take an example. Where is the 22? So, and of course, if you cannot write it this way, then it's entangled, right? I'm just looking at time. Okay, so if you can decompose it this way, it is not entangled.
It's not entangled if you can decompose it.
Yeah.
If it is a sum or things like that, and then it will be entangled.
A sum is even different.
Okay.
I will show an example to explain that.
Okay, in this case, then you call it entangled.
If you can write it as a
log of 2,
it is not entangled.
not entangled.
Take an example. Let's do matrix. Let's do it in linear algebra, and then I'll show you the quantum version. So take psi. Okay, think of it as a matrix, which is 1 over square root 2. One. This, for example. Okay, so let's see. So U, I know that U is of the form, alpha, beta, right? And V, UA and UB or VB is the form AB, right? So if I take the tensor product, right, I have alpha A, alpha B, beta A, beta B. Sorry, what am I doing? This is no, I don't want this, right? Really. I want 1, 0, 0, 1. Yes, that makes more sense. So if I take the tensor product, I have alpha A, alpha B, beta A, beta B. And so if I want this to be equal to this, right, it means that I need 1 over root 2 to be equal to 1, 0, 0, 1. And this is not possible. Right, I mean, so because if you look at the second one, it's either alpha. If I look at this one, for example, it means that either alpha or beta equal to 0. If alpha is equal to 0, it means that, of course, the first one will be 0 as well. So it's not possible. Then the other case is beta is equal to 0, but if beta is equal to 0, it means the last one will be 0. So this is not possible. Meaning what? Meaning that this which of course this is just a vector in C4, right? So which of course belongs to the tensor product of C2 and C2. So this is the 2-qubit quantum state, which is entangled. Because I cannot write it as a tensor product of 2 1-qubit states. Right? And why is that important? Because, and I'll stop after this comment, which is take an n-qubit state. So a quantum state with n-qubit, let's say psi, of course we said it belongs to C to the 2n, right? Okay, so let's see if it follows. So how many amplitudes, how many parameters do I need to describe it, Professor Bayer? Exactly, 2 to the n, right? So we need, he follows, 2 to the n amplitudes. So you could say parameters, but the alpha and beta are called amplitudes, right? Now suppose suppose no entanglement. So basically, it means what? It means that psi will be equal to, okay, let's say U, I don't know, A1, tensor product U, A2, A1, A2 are the subsystems, right? Or U, AN. Now, each U, okay, they're different, right? So U1, U2, UN, right? This tensor product is a tensor product. This is a tensor product of n of them, right? Each one of them is a vector in C2, right? So this does give me a C to the 2n vector. Let's see if it still follows. For U1, how many parameters do I need? Okay, I have 2. For this one, how many do I need? Exactly. Let's see if it was just a wild guess. For this one?
3.
Ah, see? So 2 as well. But 3 was close. Not too bad. But in the end, the point is, how many parameters do I need if it's not entangled? Right? This is not entangled, right? Because I can write it as a tensor product. I mean, and have what? 2 times n. Right? As opposed to, 2 to the n for a full vector. So, whenever you hear about exponential speed up of quantum computing, this is essentially what it refers to. Where if I have classical system, it means I put them all together. So if I want to do, I will only be able to describe a system with 2n, but in fact, with n bits of information or bits of information, I'm actually able to span a much bigger space, right? Because it's c to the 2n. Right. Yeah, sure. Sure, of course. But if I don't have entanglement, then I cannot span the whole space. If I only, tensor product, single elements, I cannot span the whole space. Entanglement means
yeah. Again, entanglement means that it was just a product of
tensor product, yeah. Tensor product.
Yeah, the tensor product of single elements.
Not entangle, yes.
Not
entangle means it's a tensor product of.
Okay.
Yeah.
And this is not entangled, right?
So the bottom one is not entangled, right? But of course, it means I'm not able to span the whole space.
Of course, but with sums of not entangled, you can get the whole space too.
Yeah, but here, because I can only. So the bottom line here is entanglement is what allows you to do much more general computations.
Sure.
That's the thing.
Yeah, and in this tensor product space, it means that these things are too sparse to be able to do anything, right?
Yeah. But so when it comes,
is that the message, or I'm trying to understand the message?
But the message is, I think the main message here is that a quantum state, if it's entangled, carries a lot more information than a not entangled state. That's the message.
Okay.
That's the message.
So in tensor product of Hilbert spaces, it's like, okay, in one thing, if you have a general sum of tensor products of the original spaces, you can span everything. And if you only concentrate on having products of guys, you won't.
Yes. But it has, we'll see that after the break, because it has hopefully it should become clear when we actually look at computations. Mm-hmm. Maybe give me 2 minutes before the break. When we will look at computations physically, and I will explain that a little bit more afterwards, but physically, what you can do on a quantum computer today, you can manipulate qubits individually. So if I have a qubit, whatever it is physically, well, I'll show some example, but whatever it is, I know how to manipulate it, which means I know how to apply unitary operations to it. I can transform it. I cannot apply an n-qubit transformation, let's say with n equal 4, for example. So I'm not able to construct physically, right, a unitary matrix of size 16 by 16, 2 to the 4 by 2 to the 4, that applies to the 4 qubits at the same time. I can do individually. So I can do this physically. I cannot do a general thing like that physically. What I can do pairwise, actually, with some, not in full generality, but I'm able to entangle 2 qubits. So I'm able to construct a 4 by 4 matrix as a physical device that will act on 2 qubits together. But I'm not able right now to build a 2 to the n by 2 to the n physical device for my unitary operator that will act on all n qubits at the same time. And so that's why this is important, because in principle, we can do a lot of computation like this. In practice, we have some physical limitations. And we're kind of in between there. Now, whether if you have a big 2 to the n by 2 to the n, whether you can decompose it into pairwise things, well, yes, but it doesn't mean that theoretically, yes, but in practice, not necessarily, and the decomposition might be very heavy. And so yes. This is
just curious. What you just tell here, it's a tensor train format. It's called quantized tensor train format. What linear algebra people.
Sorry, say again.
So decomposition of long vector in a tensor product of length 2.
Yes.
Is a so-called quantized tensor train format. What linear algebra people do already maybe 10 years. Do you know this, no?
I mean, I'm not saying this is very new, right? Mm-hmm. I mean, even in quantum, Dirac notations are not new, right? I think a lot of the computations, it's the same, in quantum, they would call it tensor product. In linear algebra, we call it Kronecker product. Mm-hmm. This is just, a formalism. I'm not entirely sure what the question is.
It's not question. No question. Sorry. I just was curious. Do you know about this developments in low rank tensor society?
Yeah. But this, yeah. Okay. So, I mean, yes, I know. I'm definitely not an expert on this. But yeah, I mean, this is a huge area. I mean, in particular in machine learning now, numerically tensor networks are extremely popular and extremely powerful. But this is a whole different world. Okay. I mean, it's called tensor or something, but it's a whole different world.
Thank you.
Yeah.
Okay. Do you have any more questions? If no, then I think we thank Jack for the first part, and we have to break now.